Hi, my name is Kuan-Chuan Peng from Mitsubishi Electric Research Laboratories, MERL. I will present our work titled Joint Training of Image Generator and Detector for Road Defect Detection. Road defects, like potholes and cracks, are a major safety hazard. Between 2018 and 2020, they caused more than 5,000 fatalities in India alone, and in 2021, they cost over $26 billion in vehicle repairs. Road defect detection systems are often deployed on edge devices with limited memory and computational resources, often no GPU. This means we cannot rely on heavy model ensembles or test time augmentation. Our key question is, can we improve road defect detection accuracy using fewer parameters and without computationally expensive techniques? Most existing methods either use ensembles of multiple models or rely on test time augmentation, both of which are impractical for edge deployment. Others use only simple low-level augmentations like flipping and color jitter, which do not produce enough variety. Some works use generative models to synthesize new defect images, but they train the generator separately from the detector. This means that the generator has no idea what makes the detector struggle, so the synthesized data might not actually improve detection performance. To address these issues, we propose JTGD, Joint Training of Generator and Detector. Our method trains an image generator and a detector together. The generator learns to create defect images that are more realistic and more challenging for the detector. The detector improves as it sees these harder examples, and this feedback loop continues throughout training. This joint training approach is the core novelty of JTGD. To ensure high image quality, we use two discriminators, one at the image level to ensure global realism, and one at the patch level to ensure local defect realism. In addition, we add a CLIP-based Fréchet Inception Distance loss, or FID loss. Using CLIP features provided a better measure of image realism than the traditional ImageNet features. This results in more realistic synthesized images for training and better detector performance. We also introduce a hard example synthesis loss. This loss encourages the generator to produce defects that the detector currently fails to detect. By continuously synthesizing harder examples, we make the detector more robust and improve its generalization to unseen data. We evaluate JTGD on the RDD 2022 dataset, which contains road images from 6 countries and 4 defect types. Our detector uses intern image T as the backbone, which is a lightweight but high-performing model. The generator is a modified cycle GAN with dual discriminators. We also use YOLO-P for drivable area detection, so the synthesized defects are only placed on the road surfaces. We use 4 A40 GPUs for training until convergence. Here, we show an ablation study on the RDD 2022 dataset. Adding the generator already improves the F1 score compared with the baseline faster swing. When we also add the CLIP-based FID loss, we gain even more. Finally, after adding the hard example synthesis loss, we achieve the highest F1 score. This shows that each component of JTGD contributes to the final performance. This table compares JTGD with the baseline faster swing on 4 countries. JTGD outperforms faster swing in 3 out of 4 countries and on the overall 6-country average. Importantly, JTGD uses less than 20% of the parameters of faster swing, making it ideal for the deployment on edge devices with limited resources. Here are some qualitative examples. On the left, we see the synthesized defects without the FID loss. Notice the artifacts around the defect boundaries. On the right, with our proposed CLIP-based FID loss, these artifacts are largely mitigated, and the defects look more realistic. This visual evidence matches our quantitative improvements in F1 score. In summary, JTGD jointly trains an image generator and detector, uses dual discriminators and a CLIP-based FID loss to improve image quality. and introduces a hard example synthesis loss to generate challenging training cases. As a result, we achieved the state-of-the-art detection performance on the RDD 2022 benchmark while using less than 20% of the parameters of the competing method, making our approach suitable for real-world deployment on edge devices. Thanks for your attention. For more details about this work, please find our archive paper below at the QR code. Thank you.